Hello and good afternoon, everyone. I hope everyone's doing great. Before we begin our session for today, I would like to know whether there are any questions regarding lecture one. Can you all hear me?
Yes.
Okay, any questions?
No.
Okay. That's good. But before we proceed, I would like to quickly recap what we have studied because I received a couple of emails asking for clarification on the first derivative and the second derivative. So I will quickly go through that. And there was one example that was left, the TSP problem, and we will try to look into that together, okay? So let's begin. This is a recorded session. So if you have any questions, just interrupt me and just ask me. Ainur, are you here?
Hello, Professor.
Hi, Ainur. Could you please take care of the students who are entering the session because I am not looking at that now. Okay, just
I'm sorry. Could you please make me call?
I have made you.
First?
And who did I make?
You made a student.
I made a student co.
Yeah.
Who is the co over here? Oh, Abebaris is the co. No, Abebaris. Withdraw co-host permission from you. I'm sorry. Ainur. Oh, that's my bad. Thank you, Ainur.
Yeah, I'll take care of that.
Okay. So I'm going to share my screen now and we will begin with continuation of lecture one. Okay, I believe you all can see this. Okay. Good. So let me quickly once again refresh your memory on the derivatives and go through those examples because I feel like maybe I was not very clear in explaining it. So I try to actually I'll try to go slow and try to break it down and make it easier for everyone. Okay, so for those of you who understood, please bear with me. But for those of you who still have doubts on this, please listen carefully. Okay. Okay, where is my pen? My pen is ready. Okay. So basically, what we want to do is we want to look at a function, okay? And the function, for example, is this function given over here. F of x is equal to x cubed minus x, okay? And what we want to do is we want to take the derivative of this function. So we know that if you look at this function x cubed minus x, how would that look? That would look like the graph shown over here, okay? And we see that we know what a slope is. A slope is a tangent that is passing at a particular point. So if you take this point, this would be the slope at that point. For example, this is the slope at this point, this is the slope at this particular point, and so forth. So if you look at a given function, f of x, and you look at the behavior or how the function actually behaves, it's very easy to visually determine the optimal points. That means the local maxima or local minimum points, okay? Because visually we can do that. I can very easily say, okay, this is a local maxima, this is a local minima, okay? But the challenge is when your function is not only dependent on one variable, but it depends on multiple variables. So you have x1, x2, x3, and you have a function which cannot be plotted in 2D. So you need a 3-dimensional, 4-dimensional space, which then would make it difficult to actually visualize and find the critical points, okay? So basically, what this function, this guy over here, I mean, this slide over here tells you is how is the slope changing for a given function. So you see that as we approach a local maxima, okay, the slope, if you look, let's look at this graph over here. So we see the slope first is high, it's a very positive value, then it slowly reduces. And once it reaches this point, okay, it becomes flat. That means the slope is 0, right? And when I say slope of a function means if I take the derivative of this function, so we know that the derivative of this function would be equal to 3x, I'm sorry, let's write x like this, x squared minus 1. So if I, for example, let's say this number over here, okay? So if I plug in this value in place of x, okay, this should give me 0 at this point because this slope is 0, okay? And then I go at x is equal to 0, you see that it has a negative slope, okay? And then again, at this point, it becomes flat. That means at this point, again, the derivative of the function is equal to 0, okay? So basically, the first derivative, which is also the slope of the function f of x, okay, tells us whether our function is increasing or decreasing. And this is good information. This is very useful information. And we will see why, okay? Now, let's move on. I have to clear all the drawings, okay. Now, we saw this example, so this is just an example. I would like to show you the example with the graph, which was the question that some students had. So this was a very easy example. I gave you a perimeter of 100 centimeters, and I asked you to find me the rectangle that has this perimeter such that the area of the rectangle is maximized, okay? So I want to find the area of some rectangle of length x and height y such that the perimeter of this rectangle is equal to 100. So I want to maximize ax, okay, given that 2x plus 2y is equal to 100. So this was what we saw over here. And I was asked, like, what is this red dot and this blue dot over here? Okay, so basically what over here, this is just an example I told you. So for example, I'm trying to analyze or study the behavior of the graph at this particular point. So if I say that, okay, study the behavior of the function at the point x naught is equal to, I think this is equal to 20, let's say 20. Okay, so that's why I just highlighted it. So this is the graph for this is the f of x graph, okay? The function, I'm sorry, not f. This is the ax, okay? The area that we want to maximize, and this is the derivative. That means this is a dash x, the first derivative of the function a. Now, so let's take a look at this point. That means the point x naught, which we said is equal to, this mouse is not working. I am sorry. Undo. X naught. Okay, so let's say x naught is equal to 20. So in this function, if I plug in 20 in my ax function, so ax was equal to, what was the function ax? Function ax was 50x minus x squared. So if I plug in 20 over here, what would it give me? 120, 400. So it would give me a value around 600. Yes, 600. So 1000 minus 400 would be 600. Okay. So what I'm saying is, okay, if I plug in x naught is equal to 20, okay, that means if I take the length of my rectangle to be 20, then it would give me an area of 600. All right. Now, but we know that that point is obviously not the optimal point, because the optimal point is over here. So which we found out to be 25. All right. Now let's look at the slope or the first derivative of this function ax. So if we keep going up, we see that the slope is positive, but slowly, if I draw the slope at x naught, which would be some line like this, slowly it would be decreasing. And at this particular point, that means that x is equal to 25, the slope would be flat, right? So if we take the derivative, we see that the slope is positive, okay? That means it is still f, you see this is still positive. Then at x is equal to 25, which is becomes 0, the slope is 0. Okay, and after that, we see that the slope actually decreases, is negative. So every point after 25 will have a negative slope. Is that clear? So this is what I have summarized over here. So I say that for every point less than 25, this is 25, okay, we have a positive slope. That means all these slopes are positive. Everything towards this part of x from 0 to 25 will have a positive slope as shown in this graph. Okay, so this is positive. Okay, and that means our function is increasing. It's going up, 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 up. For every point after 25, we have a negative slope, which is this part of the graph, and therefore our function is decreasing, which is true. And at the point 25 itself, which is equal, the slope is 0, okay, we see that this transition upward, that means the increasing slope starts decreasing. Okay, so the transition takes place at x is equal to 25. And therefore, so this point where it changes is the point of optimal value, that is 25. And we see that, in fact, to have a rectangle of perimeter 100, the rectangle should have sides equal to 25, which would obviously be a square. Okay, is it clear?
Yes.
Okay, good. Now let's go to this example. This is where I was asked to explain again. Okay, let's take this function f of x, which is equal to x cubed minus x. Okay, and so basically this is f of x, this function, and this function over here is the derivative. Okay, the first derivative of this function, which is equal to, what is the first derivative? 3x squared minus 1. Okay, so now let's look at this visually. So if I've been given this function f and I know how to plot it, I would say, okay, obviously there is one local maxima point over here and one local minima at this point. Okay, this point over here is not a local maxima, not a local minima. Okay, keep that in mind, because the slope over here, if you draw the slope, is negative. Okay, at this point x is equal to 0, the slope is negative. Okay, so we said that critical points are those points at which the first derivative should be equal to 0. So the first derivative, the slope over here is not equal to 0. Okay? It's decreasing. Therefore, we do not consider this point. Okay, so let's look at this point and let's look at this point. So the slope over here is flat, because if I take the derivative of this and I plug in this value, I will get equal to 0. So the first derivative would be equal to 0. And over here also the first derivative would be equal to 0. Now, how do we find these values? Well, as I said, what you have to do is you have to solve the equation f prime, or first derivative of the function, should be equal to 0. So what I do is I say 3x squared minus 1 is equal to 0. And I find the values of x that satisfy this equation. So can you tell me what are the values of x that satisfy this equation?
Approximately
We
25.
divide plus minus.
Okay, so we see that obviously these two values, the absolute values are the same. Okay, because this is symmetric around the point x is equal to 0. So this would be negative, this would be positive. So now what we want to find is we want to find the critical values, okay, for the function. So the critical values would be taking the first derivative and equating it to 0 and finding the values of x. So what we get is, we would get x is equal to plus minus, I have solved this, so that's why I'm just writing the final answer, square root of 3. So this is minus, or 1 divided by square root of 3, and this is 1 divided by square root of 3. Okay, now we found the critical points. Okay, so we found that this function has two critical points. So x is equal to 0 does not satisfy this. Okay, so if I put x is equal to 0, I would get f prime is equal to minus x is equal to 0. Yes, so f prime would be equal to minus 1. Okay, so I see that the derivative, the slope is negative, and therefore I cannot say that this is a critical point. Okay, is it clear? So there are only two critical points for this function, and those points are plus minus 1 divided by square root of 3. I know, please let Marat in. Okay. Okay, 1 minute, let me remember what I was saying. Okay, so now we found these 2 points. So what we have to do is Now we want to see, okay, whether this is a local maxima or local minima. Then I talked about the second derivative. So what we do now is, if we take, say, x1, let's say x1 is the negative value, positive. First, let's take the positive. 1 divided by square root of 3, okay? And what I do is I take the second derivative of f, which is f double prime, which would be equal to taking the derivative of this again, which is 6x, right? And in here, I plug in, instead of x, I put x1. Okay, so if I put x1 in place of x, it will give me 6 divided by square root of 3, which is greater than 0. It's positive, right? And therefore, what does second derivative tell us? This was a question. The second derivative essentially measures how instantaneously the rate of the first derivative changes. Okay, so it shows the instantaneous change of rate of the first derivative. So if it is positive, okay, that means over here, it tells me that we have a concave down and we are approaching a local minimum. Okay, so if the first derivative is 0, which is true, okay, and the second derivative is positive, then that point, that means x1, which is 1 divided by square root of 3, is a local minima. Okay, and if we now plug in x2 in, so now this was x1. Now if I put x2 is equal to the second value, the second critical point, I would get the second derivative to be less than 0 this time. Okay, for x2. And since the first derivative was 0 and the second derivative is negative, it tells me that this point, that means minus 1 divided by square root of 3, would be a local maximum. Is it clear? So if basically you plot the second derivative, you would get some, shit. It should be a straight line. Okay, it passes here and it passes here. So this is f double prime, which is basically 6x. And you would see that over here, this is positive. And everything over here, f of x is less than 0. Okay. So if it is less than 0, that means this part, it should be a local maximum. And if it is positive, that means this part, it should be a local minimum. Is it clear? Do we have any questions here?
No.
If there are any questions,
No
please ask me
questions.
right now. Okay, good. So everyone now understands this. So this slide basically just summarizes what I just told you.
The x equals 0, it's a point of inflection, yes?
Okay, as I told you, first, what you do is you have a function f of x, you find the first derivative, solve the first derivative equal to 0, okay? So let me write it down first for you. And we will get to, so I understood, I actually figured out where the question is, what is inflection point, what is the point of, what is that stationary point? So let me first, so if you're given a function f of x, okay, the first thing you do is find the derivative of this function, f prime x, and solve f prime x is equal to 0. This will give you all the critical points. And what are critical points? Critical points. Critical points are the points at which the derivative is equal to 0. So if you look at this function over here, the f of x in this example, there are two critical points at here and here, and we found them to be plus minus 1 divided by square root of 3. Keep in mind over here, x is equal to 0 is not a critical point because the derivative at this point is not flat. It's not 0, okay? Am I clear?
Okay, yes.
Good. And then once you find the critical points, now you want to guarantee or make sure that these critical points are local maxima or local minima or inflection point. To do that, you take the second derivative. So we take f double prime of x for all those critical points. So you plug in x, solve the second derivative and see whether they are positive or negative. If they are negative, okay, it means that it is that point, that critical point is local maxima. So keep in mind, this is opposite. If negative means local maxima, if positive means local minima. Okay? Okay. Good. So basically, so this is what you have to keep in mind. This is important. So don't mix it up. If it is negative, it doesn't mean it's local minima. Many students make this mistake. It means it's the opposite, local maxima. If it's positive, it's local minima. So this is what the second derivative tells us. And you need to do the second derivative test in order to guarantee or make sure whether the critical point actually is not a stationary point. And now we will get to what you're asking about the inflection point in an example. So let's move on now, and I will get to that. Okay. So hopefully now things are getting clear. Okay, the second question was over here. Okay, I was asked that, okay, what does this mean? And we do not understand how it relates to what you just talked about, okay? So I'm going to tell you what this means. Before we get to this, to make sure that you guys actually are following, I would like to give you guys a quick test now, test in sense, not a quiz. I just want to test your mathematical background. And so what I'm going to do, let me share my screen now. I need to. Okay, do you see my screen?
Yes, yes.
Okay.
Yes.
Now, how do we write text on this guy? Can I write something?
On near the brush, there is letter A.
Okay.
Yes.
Oh, okay. So this is the question. I want you guys to solve it right now. The tangent, because I want you guys to make clear what a tangent means. Line to some function, say f of x. Oh, I need to, 1 minute. Let me make this guy big. So the tangent line, you need me to increase this. Okay, the tangent line to some function f of x at the point, say 2, 3, passes through th, R-O-U-G-H, the point 7, 6, okay? I want you to find what would be the first derivative of that function at the point 2. So I've not given you the function, I've just said there is some function, okay? And if I draw the slope or the tangent at the point 2, 3, okay? So that means there's a function, and the function at point 2, 3 has a slope, okay? And that slope, if I draw that slope, it passes through some other point 7, 6. So therefore, the point 7, 6 does not necessarily have to be on the function f of x, okay? So I'm giving you 2 points, and the line that passes through these points, okay, is actually a tangent of the function f of x, okay, at this point. Now I want you to find the derivative or the slope at the point 2. I've actually even told you the answer. So anyone who was listening can very easily do this.
Sorry, Professor.
Yes, sir.
Did you said we should find the derivative of the slope? Because the slope of this tangent is 3/5, but derivative
Exactly.
of this
3 is what?
The slope of this line is 3/5. But you said
And
we
the
should find
derivative-
the derivative of
The
the slope.
answer is 3.
Give me
3
an
over
answer.
5
Give me
is
an
actually
answer.
the slope
Let me
of the
actually,
function.
I'm trying to draw it for you so that it's clear, okay? So suppose this is your x, oh goodness, this is going to take forever. This is x and this is your function. And suppose at point, say this is, we're looking at 2 and 3. So at this point, This is 2, 3, okay? There is, and another point is 7, 6. So say this is 7, and this is 3, 6. So let's say this point here. Okay, so this is 7, and this guy is 6. Okay, so we have a function, okay, and the function, let's say, let me use a different color. Say we have some weird looking function like this, okay, and go back to black, not black, blue. And the tangent that passes that at this point 2, 3, okay, also passes through this point. Let's say this was 7, 6. Okay, so if I draw the tangent, so if we draw the tangent at this point 2, 3, we say that the question tells you that it also passes through 7, 6. Okay, so we know that the function f of x touches point 2, 3. Okay, so 2, 3 is a point on the function. What I want you to find is the slope of this. So how do you find the slope?
Run over 6 minus 3 over 7 minus 2.
Exactly. So the rate of change of x. So if you're given 2 points, we have given 2 points. So rate of change of x over rate of change of y. Am I right? So x changes from what is x? 6 to 3. No, x is not 6 to 3.
7, 2.
It's
2 to 7.
delta y over delta x.
It is, oh, I'm sorry. It's, yeah, I'm right. You're right. It's delta y over delta x. Delta y over delta x. So delta y would be 6 minus 3, which is 3, right? And delta x would be 7 minus 2, which is 5. So the slope at this point would be 3, 5, right? So that's what I'm asking you to do. I just wanted to know whether you guys can understand. So basically the tangent at a given point is also the slope. That means it touches this function at a single point, because one of your friends asked me, what is a tangent line? So I had to explain this. So is it clear? Is this example clear?
Yes.
Yes, yes.
Okay, so I'm going to close it.
Yes.
Okay, don't save. Now,
And
you
the
see
slope is going to be the derivative, right?
I'm sorry?
Slope is going to be the
Yes,
derivative.
the slope of a function f of x is always the derivative of that function at that particular point. Okay, so at the point 2, 3, I found the derivative. So I found the derivative of the function f at the point x is equal to 2. Is it clear?
Yes.
Good. Okay, so now we get over here. This is interesting. So now I told you what does second derivative. So if your function is twice differentiable, so the second derivative, if it's positive, okay, it means that the derivative, okay, f prime is increasing in this region. So if you look at this guy, this, oh, where's my pen? Pen. If you look at this, okay, you see that the slope is decreasing. Now the question asked is, where is this related to in this figure? Where is that figure? Figure are we talking about? Over here. So the slope is decreasing. So if you take a look at the f prime, that means the first derivative, okay, that with this guy, you see that when f of x, so when f double prime of x is positive, that means if I take, so if I draw 6x, which I drew for you earlier, it was some line like this. If f of x is positive, okay, it means that this guy is decreasing. That means 1 minute, I'm sorry, I'm confused. If f of x is positive, yes, and decrease is decreasing, yes, so it's going down, true. So it means that at this point, not this point, at this point. So if if the second derivative is positive, okay, that means this part. If you look at the first derivative, you see this part, it means that over here, this slope is slowly decreasing, right? So if you look at this point, this over here, over here, you see that this is slowly decreasing. So basically we are drawing the slope, and at some point it will become equal to 0 and will give us the local minimum. So for f double prime positive, you get the local minimum. Okay. Similarly, if you see the f double prime, if f double prime is negative, you see that we would be going up. That means the slope, okay, is increasing, and then it becomes flat. Okay, so that would be basically this part. So over here, the slope is slowly decreasing till it becomes flat. Okay, so when f of the second derivative of f is negative, we have a local minimum as shown over here. Okay, so basically that's what these two tell you. Now let's look at this exercise. Yes, sir.
Sorry. When you say slope is decreasing, you mean it's approaching 0, even if it is negative? Because if it was negative, then
No. This is a positive slope which is approaching 0. Okay, and this is a negative slope which is approaching 0.
And in this case, slope is increasing or decreasing?
In this case, the slope is decreasing. I'm sorry, the slope is increasing because it's
Yes.
negative, right?
Yes. That's clear.
Okay, yes. If I made a mistake while talking, I'm sorry. Okay, so in this case, when the second derivative is positive, since we are going down, so the slope is negative, slowly it becomes 0, then it becomes positive. So we are saying at some point this transition happens. So that point is a local minimum. Okay, please correct what I said. Over here, the slope is positive and it's decreasing. Okay, that means we have plus, and then it's so they basically, if I want to draw it, I would say that in a concave down, in this case, okay, the slope is positive and we are slowly approaching 0. In the previous case, the slope is negative and we are becoming positive. We are approaching 0. So we are moving towards the positive line. Is it clear?
Yes, thank you.
Great. Thank you. Okay, so let's look at this example. This was an example of f of x. So this function over here is the f, and this function over here is the f prime, which is a first derivative. Okay. So as I told you, and again, the point which is highlighted in f, this red dot over here, is just some sample point which I want to analyze the function at that given point. So over here, my x naught is equal to 1. Okay, x0 is equal to 1. Okay, so for example, I can tell you, okay, given a function f of x as shown here, what is the functional value at x naught is equal to 1? So what you have to do is just put a 1 in this equation and find the value. Okay, but that's not the question. I had asked you guys to work this out at home, and now we will. I will ask you one by one to answer me. Let me see the names. Where are the participants? Here they are. Let's begin with Adil. Adil, are you here? Adil Kucherbayev. Ainur, please take note of students who are active and not active. Adil, I'm asking you again. Can you hear me? Asad, yes.
I just wanted to answer.
Okay. Let me randomly ask, because it seems like asking randomly serves me best, because it seems like some people just come and they are doing their own business. Adil, would you want to answer, or should I assume that you are not in the session? Okay, let's see. Danyar Musa.
Yes, I'm here.
Great, sir. Please, could you answer the first question? Where are the local maxima and minima of this function?
Okay, what are the local maxima and minima of the function? To do this, we should first find the critical points of the function and find the derivative of 5x of 4 minus 3x of 3 and minus 6x of power 2 and equate it to 0.
Yes, please keep
Uh,
talking. I'm listening.
When we equating it to 0, okay, yes, 6x equated to 0.
Okay.
We can just
Good.
we
Okay,
can just,
I understood that you know how to do it. Okay, I don't want you to do the math now. But so basically, question one is asking you where are the local maxima and minima. Now, without using the derivative approach, visually, if I want to tell you, so it would be
visually it is
so
between
this would be a local
-1,
maxima. Am I
yes.
right?
Yes,
And this would be a local minima.
local minima.
And this?
It's a stationary point.
It's a stationary point, yes, because at this point,
yes. At this point,
either
the slope is 0.
Yes, because at this point, okay, you see that, so now let me tell you another trick. So in the neighborhood, if you remember what I talked about neighborhood, so if you have a local maxima or minima, and you take the derivative of every point in some neighborhood, okay, you would see that to the left, okay, it is positive and decreasing if it's a local maxima, and to the right, it is negative and it is decreasing, right? So the slope would be opposite. Similarly over here, but at a stationary point, you won't get that, okay? So it would not be the same,
okay.
it would not be the opposite. This is just a trick, but you don't have to actually think much about it, okay? But anyways.
It means that from the neighborhood of the stationary point, from the left side and the right side, there is no like sign changes.
There is no sign change, yes.
Okay, I get the point.
Very good.
Thank you.
So basically question one is there are two optimal points, okay? These optimal points are the local maxima and local minima. So these 2 points, okay? So now the thing is, now the second question asks you, what are the zeros of this derivative? So that means if I take this as the derivative, okay, f prime would be equal to this. So the zeros would be solving this equation is equal to 0. So find all the x values that satisfy this equation. So you would get x, I have solved this for you, is equal to 0, 1, and you would get, so let's call this x1. x2 would be minus 0.7, this is a 0.66. And x3 would be 1.566. 566, okay? So that is true. Okay, so if you look at the graph, you would see that basically these are the points, okay? So at these points, x is equal to 0, okay? What is it? X is equal to 0, x is equal to minus 0.76, and x is equal to 1.566. So I get 3 critical points, okay? So these are known as the zeros of the derivative, okay? So at 3 points in this function, the slopes are equal to 0. Okay, visually I know that 2 of them are the local minima and local maxima, but this guy, the third guy, which is at 0, we don't know. So what we have to do is we have to do the second test. That means the second derivative test. So now if I take the second derivative of f, it would be, I think I have the second derivative plot here. Yes, so this would be the plot. Let's clear. Do you see the second plot? This plot.
Yes, we can see it.
Yes,
So this is f of the second derivative. So if I take the second derivative at point x is equal to 0, I would get 0. So at x is equal to 0, the second derivative would be equal to 0. And this is known as the inflection point. Okay. So basically, even though I get 3 critical points on solving the first derivative, okay? And then if so one of the critical points was x is equal to 0. So when I take the second derivative at x is equal to 0, it will also be equal to 0, right? So this point would be an inflection point. This point would be what we call the stationary point, okay? It's not a local optima, okay? Now, if I plug in the second value, so the second value was minus 0.766 into the equation of the second derivative, it would be negative, okay? So if I take f double prime of x2, it would be negative. And I said that if it's negative, it means it's a local maxima. So basically this point would be a local maxima, which is true. And if I put x3 into the second derivative, it would be positive, and that means it's the local minimum. Is it clear?
Yes.
Good.
Yes, yes.
Any questions? So you know the difference between now inflection point and what is it? Stationary point. So the stationary point, okay, is a point at which the first derivative is equal to 0, okay, and the second derivative is equal to 0, okay? True? So the first derivative over here is 0, and the second derivative was also equal to 0. So this would be an inflection point. It's not a local maxima or minima. Arasha?
Professor?
Yes, sir.
Do we use somehow the stationary points in the numerical optimizations?
When you solve a problem, as I told you, this is a very simple function, but if you have a very weird space, okay, and in that space you want to, and I give you a starting point, okay, suppose I give you this starting point, okay, not this starting point. Let's say I give you this starting point. I say, okay, I've given you a function and I give you an initial point. I want you to find the local optimum, okay, of this point. I want you to find the, let's say, local minimum of this point, okay? So what you do is, there are many methods to do this. What you do is you gradually increase the value or decrease the value and see whether the slope is increasing or decreasing. So as the slope, if the slope, so you moved in the direction where the slope is becoming flat, okay? But that's where you will get into an optimal point, am I right? Over here, the slope is not flat. So I keep moving, for example, in this direction, okay? And I come and I reach here, okay? But the functional value of this point is positive, this point is negative. I want to find the minimum. So I want to find the functional value which should be lesser than at this point, okay? Do you understand?
Yes.
So then I keep moving again, and then it decreases and I reach some point over here. I see this functional value is also greater than this point. So this is not a local minimum, right? Compared to this starting point. So the functional value or the energy over here is lower than the energy over here. So why would I want to go to a higher energy state? I am good over here and I'm stable. Now, if I keep moving and I go down, so I'll be going here and I see at some point, okay, the energy that I have over here, the functional value at this point would be lesser than my starting point. And therefore, and any point after that or before that, okay, has energy greater than that at this point. So I found a point which has the least energy. And so this would be my local minimum. Okay, so it may happen that, for example, so you understood this, so why we have a local, basically how you find the local point. Now let's assume that instead of this starting point, let me change the color of my pen. I can use, I don't know, yellow. My point is, say, let me use this eraser. Okay, yellow. Oh, and say my point is here, very close. Okay, this is my starting point. Okay, so it is positive function. I want to get to a point where it would be the energy or the functional value of that point would be lesser than this yellow point. So again, I keep moving, let's say this direction, and I reach this point. So then this point, which is a stationary point, would have a functional value lesser than this point, right? It's 0, while this is positive. So I say, okay, since this is this, I would stop over here. okay? But if I keep moving, okay, I would see that I actually find another point which is much lesser than this. But it depends on whether I decide to keep moving or I stop over here. So depending on how you look at it, I can say that this point could have been my local minima. I don't want to keep moving, okay? And I do not want to find the global minima, just a local minima. But the problem is this is not a local minima, okay? This is an inflection point. Because at this point, there is, that means if the person or the algorithm keeps continuing, we probably most likely would get to a point which is having a much more lower energy value as compared to that point. But we do not know that in advance. That's why it's very good to do the test. Is it clear?
Okay. Yes, it's clear.
Great. Any questions?
Yes, I have a question.
Yes, sir.
You said that we have two optimums, referring to maxima and minima. Was it just mistake or?
What did I say? Once again?
You said that at these 2 points, here and here, we have two optimums. Was it
Yes.
mistake or how come we have two optimums?
This is two optimal. We have an optimal maxima and optimal minima.
Optimal maxima and optimal minima.
Yeah, I mean, two
But,
optimals. When I say two optimals, I mean, depending on what you call it. I mean, I'm saying there is a peak and there is a valley.
When optimizing a function, don't we
So
have
when you're optimizing, you either say, I want to maximize or minimize. If you say maximize, then obviously this guy would be the point. But if you say minimize, then this will. I did not specify I want to maximize or minimize. I said in a function, there is a peak and there is a valley, and each of them could be an optimal point, depending on what we want to find.
Yes, I see.
Parasha?
So we can say that we have two optimals.
I would say
right?
we have two non-critical. We have two minimal optimal points. Yes, I'm sorry. We have two optimal points. Now, this optimal point could be a maxima or a minima.
Thank you.
Good. Moving on. This is a problem that I wanted to discuss before we finish, and I guess time's already running. So let's quickly do this. TSP problem. TSP problem is a very, very famous, I would say a classical problem in computer science, and it is known as a travel salesman problem. Okay, traveling salesman problem. And why is it important or why is it critical is because so far no one has been able to come up with a polynomial running time to solve this problem. That means and what is the problem? Let me first give you the statement. So the statement is that given a list of cities, so I say that I've given you names of n cities, okay? And I'm giving you the distances, Euclidean distance between every pair. That means there are cities 1, 2, 3, 4, 5, and I'm giving you the distance, okay, from city 1 to city 2, this is the distance, city 2 to city 3, this is the distance. So between every pair, I'm giving you the distance, okay? What you have to do is you have to find the shortest route or shortest path that visits each of the cities exactly once. So if I start from city, say X, I have to visit every city, okay, exactly one time. I cannot visit a city twice. And I have to return back to the city X in the end, okay? So basically I have to make a circular path, okay, starting from a city and ending to the city, to that same city, such that every city is visited only one time. Okay, so this is known as the TSP problem, and there is no polynomial time solution to this problem. The solution that exists is non-polynomial, and that's why it's called an NP problem or non-polynomial problem. That means it takes, and I'll show you, it takes 2 to the power n. So the running time is proportional to 2 to the power n, which is non-polynomial. Okay. Is it clear? Do you understand the problem statement now?
Yes, yes.
Okay, good. So I've given you the problem statement. Now I told you that there are 5 steps in actually defining or formulating an optimization problem. Before we get into this math, which is shown on the slide, let me bring a paint and let's try to find out all those 5 steps. Okay. Now, so the first step is to problem statement, and the problem statement is as such. Given a list of cities and the distances between each pair of cities, what is the shortest route that visits each city exactly once and returns to the starting city? Okay, so we want to find the shortest route. Remember that, not any route, the shortest route. Okay, so this was problem statement, and we did the problem statement. Is it clear? The second step is model parameters. We have to specify the model parameters. Well, it's very obvious from statement that if we have a set n of n cities, so say we have 1, 2, ... small n number of cities. Okay, so this is the cities. Okay, that we have in that we want to visit. And the second thing that you need to have is the distance or cost. So it doesn't matter. Let's say Cij. I use Cij to define. Cij is equal to the distance. What did I do? How did this happen?
You should change the size.
Okay, distance, okay, between cities I and J. Is it clear? So the distance between city I and J is denoted by Cij. So these are the two parameters. Step 3 is finding the decision variable. So now we have to determine the decision variable. So the decision variable obviously over here is we have one decision variable as we have seen, Xij, and it is defined as 1 if the traveler goes from city I to city J. So if the traveler decides to take the path or take the road from I to J, the Xi would be equal to 1 and 0 otherwise. Okay, so basically Xij is a binary variable. That means it takes either 0 or 1, and it's set to 1 if the traveler takes the road from city I to city J, and 0 if otherwise. So this is the decision variable. Step 4, what was step 4, anyone? Objective function, right? So the objective function would be, we want to minimize. There would be two summations. Come on. So Control Z is okay. The Control Z is easier. Okay, we have two summations. So the first summation is I from 1 to n. Second summation is I from 1 to n, okay? Xij times, this is times, okay, let's say multiplied by Cij. Is it clear? So I want to minimize the distance that I travel from any city I to J. It's given that I have to visit every city only once and return back to the actual city. Okay, so I want to minimize this function. Is it clear? And finally, the fifth point, or the last one, is determining the constraints. So now what would be the constraints? I want you guys to think and tell me. Guys, someone, I said you wanted to help me over here. Tell me.
Limits?
Okay, what limits? Tell me, give me the formulation. So if you do not know how to formulate it, just tell me verbally. What would be the constraints?
We can't
We
visit.
can't get the same number.
I'm sorry?
Can we get the same number on whether it's the same city or not? Like we cannot return to it again, right?
Yes. So what does that mean? So there will be two constraints, okay, that comes to our mind. The first constraint is that the traveler should enter each city exactly once. Am I right?
Yes.
Okay, so this is one constraint. So if I want to enter each city exactly once, that means xij, summation of xij should be equal to 1. Okay, for j from 1 to ... n. And over the summation, I have I from, 1 to n. Okay, so starting from I should enter every j only once. Okay. And the second is, again, I should leave every city exactly once, right?
Yes. Yes. Yes.
Isn't that beautiful? So now I have a constraint. So if I enter a city exactly once and I leave a city exactly once, I can say that I will find a path. Okay, I will find a path, because if it is more than one, it means that I have visited or left the city more than one time, which is not allowed. Okay, so then over here I would have just the opposite. J from 1 to n for all i's equal to 1, 2, 3, ... till n. Okay, so I have two constraints. Is it clear?
Can I ask here?
Yes, sir.
Isn't the second condition redundant? I mean, if we visit only once, it is natural that it is obvious that we can leave it only once. Or
What is a guarantee
physically,
that if you enter a city once, you leave it?
what guarantees?
Okay, I know what your question is. Could you just hold your question till I tell you the problem with these constraints, and we will try to solve it. These constraints are, I mean, we call them local constraints because they seem to work, but I will give you a scenario where actually, if I execute these local constraints, I do not get shortest path, okay? And then you ask me the question if I've not answered your question, okay?
Okay. Then another question.
Hmm.
Can we put such conditions that the starting point or leaving point should be the same as the city to which you entered the last?
The starting point, not necessarily. Why would you want to do that? It makes, I mean,
Well,
it doesn't.
I mean,
teleportation is not
like
possible.
so that jumpings are not allowed.
Yes, we cannot teleport.
Okay, I know what your questions are. Okay, and I understand, but I need to explain, or I need to tell what the problem is with this. I show you an example, and then if you do not understand, then ask me again. Okay, I know what your questions are, so just give me 2
Yes.
minutes. Okay, I'm
Yes,
going to
thank
answer
you.
them.
Thank you.
Okay, so now we have two constraints. So basically, the thing that comes to your mind is I have a set of nodes. In order to make sure that there is no, I mean, to what we say, impose the requirement of the problem, every node should be visited once. That means when I enter it once, that means every node is entered once and left once, right? So what happens is we can put these two local constraints. We say that for every city that we enter, okay, we should also leave it. Okay, we cannot stay in that city. Okay, and I'll tell you why this is important. But the problem with this is that there is a problem with this constraint. Not with the constraint itself. We need to add another constraint to actually complete the constraint, to guarantee that it solves it finds the shortest path. So there is one constraint missing over here, and I'm going to tell you what it is once I tell you what actually is the problem with only having these two constraints, okay? Okay, let me get back to, where is this? The slide, so you see this? Okay, so as I told you, these were the constraints, and this is what we discussed. Can you see my screen, guys?
Yes, we can.
So these were the local where's my pen? 1 minute, pen. Okay. Why is it? 1 minute, stop sharing. 1 minute, guys. Okay, do you see my screen now? Okay, so this was the objective function. Oh, not yellow, red. This was the objective function, and these were the two local constraints, which we said if it enters. So it leaves a city once and it enters a city exactly one time. But as I said, there's something missing. And what is that missing? I can tell you only if we look at the example that follows. So assume that you're given this graph, okay? And so there are 6 cities over here, the nodes, and these are the distances between them, okay? So let's say it's a directed graph. And in this directed graph, so let's say we start from city 5, okay? If I go from city 5, let's start from city 1 itself, okay? Let's go according to the increasing value of the number. So city 1, I can go from city 1 to city 5, okay, right? Because there's no other path which is shorter than this. If I go through city 4, it would be 9. City 5 has 1, right? So I take city 5. Again, from city 5 to city 6, the shortest path would be 1. So I take this guy. And then from 6 to 1, again, the shortest path would be 3 because 7 plus 5 is greater than 3. So I would take this. Okay, so now I visited 3 cities over here. Okay, next I want to go to another. So we have done 1. So let's start with 2. 2, I go to city 3, 4, and 5. So the blue highlighted paths, the blue ones, actually is a TSP problem saying that I'm visiting every city exactly once. Okay. And I'm returning back to that actual city, okay? So over here, I'm starting from 1 and I'm returning back to 1. Over here, I'm starting from 2 and I'm returning back to 2. So if I have those constraints that I just showed you, that means these constraints, okay? I would get this. That means given a bunch of cities, I do not find one single shortest path, but I may find multiple sub paths, okay, which actually satisfy this. So the problem that, the constraint that is missing is that we should be able to connect each sub path with each other. So I get basically 2 partial tours. Tours means those paths or sub paths or tours. I get 2 partial tours which satisfy these conditions, and it minimizes the objective function. Is it clear? So now the problem is, so the missing link or the missing constraint is somehow we have to get rid of or eliminate subtours. Okay, and that is known as the subtour elimination constraint. And that constraint itself is the only reason why solving the TSP problem is non-polynomial. That means it has 2 to the power n possible situation or combinations that it has to check, and checking those combinations actually increases the running time of this objective function. Okay. Now, so I have to add the constraint in this blue box. Now, what does this constraint tell me? Okay. This constraint was proposed by 3 people, DFJ, I don't know, Danzig, Fulkerson, Johnson. You can Wikipedia this guy and you can find it. So it's known as the DFJ constraint or the subtour elimination constraint, okay? And what does it say? It says that for every set S, okay? So say that we have a set S. Let me use my pen. So for every set S, so this is a set S of cities, we have to add a constraint which tells us that the tour or this should definitely leave this S. That means it should connect the city in this S to some other city which is not in S. That means we should have a connection between these 2 subsets. Is it clear? So the DFJ constraint or the subroute elimination constraint here tells us that there should be for every S. So what is the value of S? So S can be, let me write it over here. So for every set S, which is a subset of N, and N was our set of cities. Okay, so for every subset S of N, okay, where S can take values from 1 so the size of S can be either 1 or it should be N minus 1. It cannot be N, that means all the cities are in the same set. That means that all of them are connected. So we should have two, in order to have two subsets. So we should have either one city and all the other cities separate, or we should have all the N minus 1 cities over here and one city over here. So we should be able to find the link between them. Is it clear? So we are saying that, so that this constraint says that for every S, okay, that is in V over here, it's V, we took it to be N, okay, in our formulation, I denoted V by N. So it's the same thing. And for every, well, this can be also equal to 1, depending on the definition, I have used it to be 1. So if the size of S is 1, or is some value between 1 and N minus 1, okay, then what should we have? We should have the summation. Let me write it down. Let's go back actually to my paint. Okay, so if I write it down over here, clear, I do not need here, I need my mouse, and in my mouse. So the thing that I add over here is for every S, set S that belongs to N, where S takes values from 1 to N minus 1, okay? The summation, there are two summations. So the first city, I, should belong to S. So so any city I that is in S, for every city I that is in S and every city J that is not in S, so this is not in S, okay, Xij should be greater than equal to 1. That means there should exist at least one connection connecting a city in S to a city outside S. Okay, and so with this, I eliminate or I get rid of these sub-tools or the small subpaths, and I make sure that we have one big shortest path, connected shortest path. Okay, is it clear? So this constraint that I've written over here is basically the same as what is written over here, but in a different way. Okay, so it's the same thing, don't worry. So let me give you an example. Okay, so let's go back to MS. So can I extend this somehow or go somewhere?
I cannot see paint.
Huh?
I can't see your paint. Sorry for that.
You cannot see my paint?
Yes.
Okay, let me, where is it? Share paint. Can you see it now?
Oh, yes. Yeah.
Okay, so this is the constraint that I added. So I'm saying for every set of S that can be of size 1 or up till N minus 1, double summation, okay, for every city I that is in the set S, and every city J that is not in the set S, there should exist at least one link connecting I and J. Okay, and this constraint, when you add, solves the problem. But the problem is when you add this constraint has to check 2 to the power N number possible combinations. And I'll give you a very short example so that you understand that. So, for example, let us say that we have two cities, city 1 and city 2, okay? This is a very basic example. Okay, so in city 1 and city 2, so if S can be 1. So let's say we take this set to be S. City 1 is in S and city 2 is not in S. Okay, So what are the possible combinations that we have to see? So we have to see how we can connect them. So basically what we have to do is we have to find all the possible subsets of a set with two cities. So it would be either a 1, 2, or 1, 2, right? Am I right? So these are the subsets, 1, 2, and obviously the empty set is also there. So if we have a set of size 2, there would be 2 to the power 2 possible subsets, right? Which is 4. So in our case, we have 4, okay? And out of this 4, I said we cannot have this and we cannot have this. So it will be to the power 2 minus 2. So we have only 2 possible cases. So we can leave 1 by going to 2, and we can come back to 1 by coming from 2 to 1. So this would be the path, right? Is it clear?
Right.
So we have 2 to the power 2 minus 2 possible cases. Now let's say we have 3 cities. 1, 2, 3. 1, 2, 3. Now if I take S, so let's see what are the possible combinations, okay? So I can have city 1, or let's just write numbers. City 1 in S and cities 2 and 3 not in S, right? Or I can have cities 2 in S and cities 1 and 3 not in S. Or I can have city 3 in S and cities 1 and 2 not in S. Am I right? Now, other than this, I can also have cities 1 and 2 in S and city 3 not in S. Okay? How do we increase the size of this guy?
Sorry, but if there does not exist a pass between one cities.
There is always a path.
No, I mean direct pass.
If there exists no direct path between one city,
Yes, yes, yes.
if there exists no direct path between one city.
I mean, if there is no direct pass between cities, like
Okay.
there is no direct pass from 1 to 3, you should go from 1 to 2 and 2 to 3. Should we consider
Okay.
this condition?
So you're talking about a condition where you do not have a direct path from one city to another city, and you have a direct path from, so that doesn't matter. So if you do not have a direct path from one city to another city, the the Cij value would be infinity in that case. So that means you have to go from one city to another city. So it doesn't, so you can draw a line, but you can put the weight equal to infinity. Do you understand?
Oh, okay. Okay.
It takes care of that scenario. Don't worry, it does take care. So if you just write Cij is equal to infinity, so we assume that we have a complete graph or a complete network, and if there is no direct path connecting two cities, you just put the weight of that path, that link, to be infinity. Okay. So obviously you'll always use another path. As I showed you in the example, you always use a path which is the shortest one. You do not use the one which is having even if there is a direct path, but the weight is highest, you do not take it because you're finding the shortest path. Okay.
Oh, okay. I get the point. Yes.
So 1, 3, and what else? I've written it down. Let me quickly write it. 1, 3, and 2. So 1, 3 is in S and 2 is not in S. And finally, the last one would be, what is it? 2, 3 in S and 1 not in S. Okay. So basically we have 3 cities. So we have 2 to the power 3 and the minus 2. Okay. So it would give you how many? 6. So we have 1, 2, 3, 4, 5, 6, right? So we have to look at all these possible conditions sets. So each one of them in this final constraint. And to do that, we have to have an order of 2 to the power n minus 2. So 2 to the power n minus 2 is the running time of this constraint itself. So which ensures that there is no subroot. So that's why this is a non-polynomial problem, NP problem, and it takes a non-polynomial time to solve. Okay. Okay, I guess we should stop because I have a class now. If there are any questions, please email me or keep them and save it for Thursday, and I will try to I will answer them on Thursday. So on Thursday, we will start lecture number 2. Lecture number 2 is basically solving univariate problems, okay, which we look at some very basic approaches that are used to solve univariate problems. Any questions so far?
No.
Okay, so if there are questions, please ask me, save them and ask me on our session on Thursday. Okay, thank you very much, guys.
Okay, thank you, Professor.
Screening has stopped sharing. Yes, stop sharing and take care of yourself. Study well. And this week I will upload some tutorials or some sample exercises so you guys can work out. And if you have any questions, we can also discuss that later on. Okay. So please, and also what I'm doing is I'm migrating all my videos to a channel which I've made only for my courses. So I will share the link of the channel and the playlist. So you can please always check that for new videos. For example, this recorded video will be put up there. Okay, I will send you the link of the playlist. So it's up to you to check for the updated videos. Okay, guys. Thank you. Take care and see you on Thursday. Bye bye.
Thank you. Bye, Professor.
See you. Bye bye.